Hello, everyone. Welcome to the ILTA Physics online problem solving lecture. Today, we are going to study gravitational orbits, which explain the motion of celestial bodies. The orbital motion of a satellite can be thought of as a very large circular motion on a cosmic scale. The picture below shows the ancient Greek geocentric view of the universe. They believed that Earth was the center of the universe, so when they tried to explain the motion of the rest of the stars, they must have run into some difficulties. Now, based on the general concepts of gravitational orbital motion today, let us think about the correct motion of satellites. A satellite experiences a constant downward pull due to the gravity of a massive planet, but it never actually falls. Instead, it is a unique type of motion where that gravity acts as a centripetal force, causing it to move in a circle. The basic types of problems we will cover today will involve solving questions related to the gravitational attraction between a planet and a satellite based on Newton's law of universal gravitation and the resulting circular motion created by the centripetal force. We will also solve problems regarding periods and radii based on Kepler's third law, which explains celestial motion. First, let us briefly summarize the orbital motion of a satellite. Orbital motion is created when the gravitational force, the attractive force between objects, and the motion balance out to produce a circular path. Generally, celestial bodies that revolve around a large planet in a circular path are called satellites. The reason a satellite can move in a circular orbit around a planet is that the gravitational pull from the large planet acts as a centripetal force that constantly changes the direction of the satellite's motion, creating a circular path. As shown in the diagram on the right, when a satellite is moving at a certain altitude around a planet with a large mass, the attractive force pulling it toward the planet acts as the centripetal force for the satellite's circular motion, resulting in an orbital motion with a circular trajectory. In this kind of orbital motion, our main interests are usually the speed and the period of the satellite. First, let us look at the speed that allows the satellite to maintain its circular motion. The speed of a satellite can be derived from the relationship where the gravitational force from the law of universal gravitation equals the centripetal force of the circular motion. Let us calculate each one based on two different perspectives of looking at the same force. According to Newton's law of universal gravitation, the force with which a planet pulls a satellite can be expressed by the following equation. Gravitational force equals the universal gravitational constant, capital G, times the mass of the planet, big M, times the mass of the satellite, little m, divided by the radius squared. This force acts as the centripetal force for the satellite's circular motion. For the circular motion formula, the centripetal acceleration can be calculated as the velocity squared divided by the radius. Multiplying this by the mass of the satellite gives us the centripetal force. These two equations represent two ways of looking at the exact same force. Therefore, if we set the two expressions equal to each other and solve for speed, the speed of a satellite in orbital motion is simplified into the following equation. Velocity v equals the square root of the universal gravitational constant g times the mass of the planet, big M, divided by the radius, r. The interesting part is that the mass of the satellite does not matter at all when it comes to its orbital speed. The idea of analyzing a satellite's orbital motion as circular motion can be used to derive the relationship between the satellite's orbital period and its orbital radius. The speed of circular motion is equal to the distance traveled in one full orbit, which is the circumference, divided by the period, which is the time it takes to complete one full revolution. Now, if we substitute this into our previous speed formula and rearrange it, the period squared becomes proportional to the radius cubed. This relationship, known as Kepler's third law, often appears as a common problem type in satellite orbital motion. Now, let us solve some related problems. Problem number 48 is about the periods of planet X and planet Y, which are orbiting a planet named Omega. It says that 1 year for planet X is 200 days, and planet Y is located 4 times farther away than planet X. Here, 1 year for a planet refers to its orbital period. It is just like how the time it takes for Earth to complete one full revolution around the Sun is defined as 1 year. Let us consider the relationship between the periods of the two planets orbiting at distances where the radii of their orbits are r and 4r, respectively, as shown in the diagram below. According to Kepler's third law, the period and the radius have the following relationship. The period squared equals a certain constant value times the radius cubed. Since we do not need to calculate the exact numerical value of this constant prefix here, we'll just label it as a capital letter K. Then, the period of planet X can be written as the following expression, and that equals 200 days. Now, let us calculate the period of planet Y. Since its orbital radius is 4r, if we substitute this into the equation and calculate, it turns out to be 8 times the period of planet X. Therefore, multiplying 200 days by 8 gives us 1,600 days. This problem can also be approached and solved by directly using Kepler's third law, that the period squared is proportional to the radius cubed, and using the ratio between the periods and the radii of the planets. For those who are interested, I encourage you to try solving it this way yourself. Problem number 49 asks us to find the period and speed of the space station orbiting at an altitude of 250 miles above Earth. Let us picture Earth and the space station in orbital motion, just like in the diagram on the right. One thing you need to be careful about in this problem is that the altitude of the satellite is given as 250 miles. But this value is not the actual radius of the orbital motion. As you can see in the diagram, the altitude is 250 miles from the surface of Earth. So you just need to make sure that you add the radius of Earth to the altitude of the satellite to get the total radius of the satellite's orbital motion. All right, let us find the radius first. The radius of Earth is 6,370 kilometers, and the altitude of the satellite is 402 kilometers. Converting the 250 miles given in the problem into kilometers gives us 402 kilometers. Adding these two values together gives us the radius of the satellite's circular motion, which is 6,772 kilometers. If we convert this into meters, it becomes 6,772,000 meters. In this problem, we can use two formulas: the formula for speed and the formula for the period of gravitational orbital motion. Since the problem asks for both speed and period, we do need to find both. However, looking at the structure of the equations, it is clear which one is easier to solve first. Finding the speed first, and then using that calculated speed to find the period makes the math a bit simpler. If you try to find the period directly using the radius, you'll have to deal with calculating square roots and cubes. Now let us find the speed of the satellite. The speed of the satellite can be written using our previously derived formula. Velocity equals the square root of the universal gravitational constant, g, times the mass of Earth, divided by the radius. If we plug the given conditions into this formula, the speed of the satellite comes out to 7,672 meters per second. Since we now know the speed, let us find the period of the satellite. The period is found by dividing the circumference of the orbit, which is 2 times pi times the radius, by the speed. If we plug the corresponding values into this equation as well, we get 5,547 seconds. Converting this into minutes gives us 92.45 minutes. Today we solved some basic problems regarding the orbital motion of satellites. Please make sure to memorize the two related formulas we used today, the speed formula and the period formula. and practice applying them to different problem conditions. That is all for today's lecture. Excellent job, everyone. I will see you all next time.